In the last class, we discussed the role of feedback and forcing, and I showed this slide in which you show clearly how, starting from the current climate, when you double CO2, there is an imbalance at the top of the atmosphere. That imbalance is immediately adjusted by Earth temperature going up by 1.2 degrees without feedback, just due to CO2 increase alone. And after many years, water vapor and other quantities change, and the system finally comes to equilibrium again at 240. And so you can see that the forcing causes the initial change in temperature that leads to further changes, which after many years reaches a new equilibrium in which both forcing and feedback contribute to temperature change. Now, the best way to illustrate this is to show how the change in net radiation, which was caused by the forcing, slowly reduces in time as the temperature of the Earth increases. After a couple hundred years, the system will reach a new equilibrium where the net radiation change is 0. Okay. It will not go down smoothly, there will be up and downs, because remember, energy is being exchanged between ocean and atmosphere continuously. There are imbalances occurring there. So, there will be year to year fluctuations that we saw in the last lecture. I'll highlight that here. You can see here, so in this figure, the year to year changes in global mean temperature is not climate change, it is climate variability, because in the Earth system, energy is exchanged continuously between ocean, land and atmosphere. And due to these adjustments, in some years temperature is higher, in some it is lower, and this is a natural fluctuation of the order of half a degree or so. So, this is not, when we talk about climate change, we talk about average over 10 years or 100 years, in which case these will get completely smooth. So, you see that temperature went on increasing in response to the increase in CO2 and water vapor, and finally after hundreds of years it started fluctuating little bit, which is natural variability, and the new equilibrium, this is 0. Now, this shown more clearly in a recent IPCC report, showing we start with a 4 watts per meter square imbalance due to a sudden increase in CO2, and after about a year temperature changes by about 0.7, then it goes on increasing, and as you go in time we ultimately reach a state of equilibrium where there is some fluctuation of the order of 0.1, 0.2 degrees, but the net radiation at the top of the atmosphere has gone to 0. The perturbation has been reduced to 0. Now, let us define some parameters which are routinely used in this field. The temperature change is written as equal to a parameter called lambda, the climate sensitivity parameter, into forcing, which is in watts per meter square. Therefore, the units of lambda is Kelvin change per 1 watt a meter square. So, it tells you the Earth system, for 1 watt a meter square change, how much is it change in global mean temperature. Okay. Now, this is a very important parameter, because we know that when you double CO2, we change the forcing by 4 watts a meter square. So, we would like to know for 4 watts a meter squared how much is the temperature change in the global mean. Okay. Now, I want to warn you that unfortunately some people define lambda as not delta T with delta F, but the other way around, delta F by delta T, in which case we will call it watts per meter square per Kelvin feedback parameter. So, there is a sensitivity parameter, there is a climate feedback parameter, one is the inverse of the other. Okay. So, through units you should be able to know which one are they talking about. Okay. Now, to understand this approach, let us see how the system works. Initially you give a perturbation, like you double CO2 and the temperature goes up by 1.1. Okay. After some time the feedbacks kick in and whatever goes up, cloud changes, albedo changes, so temperature changes further. Okay. This is called feedback. Initial perturbation and this is a feedback. Okay. This is response without feedback, this is the feedback. If you add these two, you get the total temperature change. So, the non-dimensional parameter f is defined as feedback by final delta t. Notice it is not feedback by the initial delta t, but feedback by final delta t. So, using this definition I can rewrite this as delta t equal to T0 f times delta t. Okay. And they can take it to the left hand side and then delta t becomes delta T0 by 1 minus f. Okay. Now, this tells you something very interesting about the final temperature change. The final temperature change will be very, very large in response to initial change if f is close to 1. Okay. If f is close to 1, then delta t feedback is much larger than delta T0. Okay. And so, this will increase a lot. So, f value, which is a non-dimensional number, if it is very small, we are lucky, the feedback is not large. So, the initial perturbation will not lead to a large change, but if the feedback is large, 0.5 or higher, it will amplify the initial temperature by a large margin. So, this is a cause of concern today, as we will see in this lecture and the next lecture, that a feedback parameter anywhere around 0.5 implies doubling of the initial perturbation of the Earth's climate, which is a cause for concern. Now, if f is positive, we call it a positive feedback because internal changes amplify the temperature response. If f is negative, the denominator will go up, this will go up, and so delta Ts will not increase that much. Okay. Now, we can talk about many feedbacks or one feedback like albedo and water vapor and clouds. So, we can extend this derivation to 1 minus sum of all feedbacks. So, this f is sum of all feedbacks. You can look at each feedback separately and see how much it contributes and take the sum. Okay. Because we need that, because we need to understand the various feedbacks like clouds, water vapor, albedo, and know the contribution of each and whether they are positive and negative and how they add. Now, let me plot that result I showed you in the last slide as the total temperature change from the initial perturbation called the gain. This is in the language of electrical engineering, gain of an amplifier. Okay. So, the gain shows you how much amplification occurs, and that is 1 by 1 minus f, and you can see that it is a very non-linear function. If f is small, it is linear. As f approaches 1, it becomes very, very large. Okay. If g is less than 1, that means f is negative. The response is damped, it is called negative feedback. If g is greater than 1, response is amplified, called positive feedback, and g is greater than 1, it is of course unstable. It's called an explosive feedback or runaway. System is completely unstable. Now, the concern we have today is our knowledge about the mean value of f is not very accurate. So presently, it is believed that mean value of f is somewhere between 0.3 to 0.65, is around 0.65 with a uncertainty of 0.3. Okay, that means it is anywhere between 0.35 to 0.95. Okay, so because of this, we can predict that there is 29% chance that it is between increased temperature may be between 2 to 4.5. That is 14% chance it is between 4.5 and 8, and there is 13% chance it is greater than 8. Okay, so this is very bad news because Earth will be not livable at this temperature change. On the other hand, for the same mean value, if the uncertainty is smaller, then we are in this range which IPCC normally quotes, which is higher. For example, if sigma f is around 0.1, then there is 55% chance that we are in this range. And if sigma f is as low as 0.05, we can say with 95% confidence that will be in this range. We want to be here, but mostly we are somewhere here. Our climate models are not good enough to bring down the value of sigma f to sufficiently low value that we can say with great confidence that we are in this range. This is ongoing area of research, a lot of work is going on, but we are not yet able to bring down the uncertainty in f to around 0.05 so that we can say with 95% confidence that the temperature change will not be beyond this range of 2 to 4.5. Now, why is there such a large range of value of f in the climate models? Because today's climate models, although they are very sophisticated and advanced, they have a lot of parameters which are not accurately known. For example, the fall speed of ice is not known, we specify a value. The critical relative humidity when the clouds form, we do not know accurately. Okay? At what rate does a cloud droplet become rain? We do not know accurately. It depends a lot in different parts of the world and depends upon the kind of cloud and rain. Okay? And the calculated cloud fraction has some inaccuracies. Now, the other problem is as air parcels rise in the atmosphere, some amount of air is entrained, gets into this parcel, and it affects the rate at which clouds form. Okay? And this is not accurately. And in the radiation calculation, we do not know accurately the ice particle size and shape. We do not know about the cloud overlap that occur in the real atmosphere. There is some uncertainty about water vapor absorption bands. I will talk about it later. And there is of course uncertainty about turbulent mixing in the atmosphere. There are uncertainty about waves in the atmosphere due to mountains called gravity wave drag. And then there are uncertainties about roughness in the forest and roughness in the canopy and so on, and how much CO2 is coming out of plants, and albedo of ice and heat transfer ice. So, a lot of parameters are unknown which are given some numbers arbitrarily. Okay? So, one of the scientists decided to see how the climate model response changes when you change these unknown parameters by a small amount. Okay? So, this shows how the climate sensitivity, that is the impact of doubling CO2, how it changes in response to change in some of these parameters. Okay? The black line is the prediction from a project called climateprediction.net, where a scientist asks hundreds of people to run a climate model with slightly different parameters. Okay? Small change in the value of f, the feedback parameter. And he got thousands of results and he plotted them as a distribution curve. So, what this shows is that there is 10% chance that temperature change may be as high as 6 degrees. There is 1% chance that may be as high as 9 to 10 degrees, although the most probable chance is around 3 degrees. Okay? So, we should expect that doubling of CO2 will cause about 3 degree warming, but there is a small chance that may be 6 degrees or 9 degrees. This is the main issue under discussion in IPCC and the global negotiation, because if there is a small chance that warming as high as 8 degrees, it is very bad news, because Earth will be almost be not livable for human beings. But if you are a person who does not believe in extreme situation, you think that most probably it is around here, although it is only around 50%, you may say, well, I will assume this is what will happen. But there is a small probability of very large changes, which we are not able to at present rule out. We cannot rule out this. This also shown another way, that as you run the model for hundreds of years, the probability of very high change goes on increasing. Okay? The mean may say 2 degrees, but there is a small probability of 4 degrees also, okay, because of the uncertainty in the feedback parameter. Now, this can be shown more clearly. You plot the 1 by 1 minus f curve and ask how a small change in f causes a change in delta t. If f is small, then a small change in f will not cause large delta t. But as you go closer to large values of f, a small change in f, the same small change here causes a large change in delta t. So, we would like to be somewhere here, but as far as we know, we are somewhere here right now, and there is also a fear or a possibility that we are somewhere here. So, this is where there is so much of debate and uncertainty about how climate will change. And this can be shown in terms of the probability of error in the estimate of f's, the probability of the error in the predicted temperature change. You can see that this is highly asymmetric. This is symmetric. I am assuming that 0.65 is my mean value and it changes by plus or minus 0.14. Okay? But the response here is one sided. The chances of high temperature change is always there, but chances of low temperature change is very small. This is what of a great concern. The asymmetry in the temperature response due to uncertainty in the value of f is what is causing so much of lack of agreement among countries. Okay. So, we come back to the feedback analysis. We say that for doubling of CO2 without any feedback except the Planck feedback, that is Stefan Boltzmann's law, is around 1.1 to 1.2 depending on the model. Okay. If you add all the other terms which depend on temperature, like albedo, water vapor, clouds, then this quantity adds to this quantity. Okay. The Planck feedback, nothing but you differentiate this term, the outgoing longer radiation, for no feedback, you get 4f sigma Ts cubed, and for the present temperature of 288 Kelvin and assuming f value of around 0.61, the present value, you get around 3.3 watts per meter square Kelvin as the feedback parameter. Okay. So, now we look at an alternative way to look at feedbacks. Here delta R is the perturbation to the net radiation at the top of the atmosphere, and the Earth's response to that is a change in global mean temperature on the right, and this change in global mean temperature causes a change in the net radiation. This is the feedback, okay? And this C1, it tells you how change in delta T causes a further change in delta R. So, now the new delta T becomes the old delta T without feedbacks plus an additional term due to change in delta T. Okay. So, we look at this further. So, additional radiative forcing due to the changes in the system, and so you get a new value of delta T. And if you rearrange this equation, you see that the delta T is linearly proportional to the original delta T without feedback, and 1 minus C1 into lambda 0. So, this quantity is what we, in the early derivation, we call it as the feedback factor. This is a non-dimensional quantity. C1 has a dimension, lambda 0 has a dimension, but C1 lambda 0 is dimensionless. And so, if you go back and define gain as before as delta T by delta T 0, okay, then we get the same result, which is delta T 0 1 minus F. So, this is an alternative derivation which some of you may find it more easy to understand than the previous one. Now, once you understood this, you can extend this to multiple feedbacks. We add one more term here, one more feedback. Say the one is this is water vapor, this is lapse rate, changes in the gradient of temperature in the vertical. Then the same analysis goes and you have second term here, okay. And this way you can proceed to any number of feedback parameters. But ultimately we need to derive these feedback factors from actual complex climate model, okay. And what it is done there is the model is run many times keeping one of these things constant. I gave one example from the work of Manabe, where he kept water vapor constant after doubling CO2 and showed that the response was different. Similarly, you can keep clouds invariant or sea ice invariant or snow cover invariant and run the model again and see what changes are there. So, through that you get these partial derivatives, how the net radiation is changed by changes in one of the parameters, okay, and thereby derive these quantities. Now, lapse rate is an important feedback in the Earth climate system because the temperature of the atmosphere decreases with height, okay, and that quantity in the tropics is around 6.5 degree Kelvin per kilometer today. But as the global warming proceeds, that rate of change of temperature with height will change, and when that changes, the upper part of the troposphere will warm more than the surface, and if that happens, then the gases in the upper part troposphere will be able to emit radiation to space much better than before. So, that leads to a negative feedback, that is, the changes in lapse rate that occur due to global warming enable the Earth atmosphere system to lose more heat to space than earlier. So, it helps to provide a negative feedback and stabilize the system, okay. So, so what this shows here is that the original lapse rate was this, and after the doubling of CO2 the lapse rate changes, and due to the change in lapse rate the upper portion of the atmosphere has a higher capability to emit radiation to space. Okay. Now, there is a connection between lapse rate change and water vapor change. Water vapor feedback is one of the most important feedbacks in the Earth climate system, because as soon as the temperature of the atmosphere increases, the amount of water vapor will increase by laws of thermodynamics. Okay. And so, if the temperature in the upper troposphere increases, it has impact on water vapor. So, one can see from one of the models there is a correlation between change in lapse rate and change in water vapor. So, these two should be looked at together, they cannot be looked at independently. So, here is an example where you can put all the lapse rate together and you get back and the old formula we had derived earlier. Now, this shows the clear relationship between change in water vapor, change in temperature of the global mean Earth temperature with change in total column water vapor from surface to top of the troposphere, and see that they are well correlated, and typically a 1 degree change in global temperature causes a 7% increase in column water vapor. So, this is one of the important positive feedbacks, because as the temperature of the Earth increases, more water vapor is there in the atmosphere, that causes more greenhouse effect, it traps more radiation, and so the temperature will increase further. So, water vapor is a positive feedback and lapse rate change is a negative feedback, and so it will slightly counteract the role of water vapor. Okay. Now, let us summarize the various changes that are taking place. You double CO2, you get an additional greenhouse effect of 4 watts per meter squared. So, net radiation decreases at the top of the atmosphere, and it causes 1.1 degree change, we saw that. It increases water vapor, which causes additional 5 watts per meter squared trapping of heat. It melts snow and ice, additional 1 watt per meter squared heat absorption. It changes clouds, this can be the positive negative. In this example, it is positive 1.5. But changes in lapse rate, that is the change in vertical profile temperature, causes a negative feedback. These two cancel out approximately. So, the original 4 watts per meter squared net radiation change caused by CO2 increase is increased by 6 watts by these two, and you will get a 10 watt per meter squared change, and which causes finally approximately 3 degree warming. So, this shows how the various feedbacks either add or subtract to the initial perturbation. Now, among these various causes, the most important cause is cloudiness, okay, most important uncertainty we have. So, we will discuss that in some detail in the next lecture. Thank you.